Assalamu alaikum wa rahmatullah. Today our class is all about designing parallel programs. Inshallah, we are going to continue from what we have stopped on last time. So last week I explained to you how to make how to build a simple parallel program using C# and Visual Studio. So today, inshallah, we are going to understand the concept of making things parallel. I mean, how to design the parallel programs. Okay. So the videos, records of my classes will be all uploaded on the Facebook. So please visit it and subscribe if you can. Inshallah, all the tasks will be also uploaded on the Blast. So please follow the updates. And for today, inshallah, we are going to start with the designing parallel program. Designing parallel programs. Actually, we have about 10 subcategories, or 10 subtopics in our agenda to cover. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 topics. So we cannot cover them all in this class, but hopefully by the end of next week, all things will be covered, inshallah. So today we try to cover the first 3 or 4 topics, inshallah. And let us start with the automatic versus manual parallelization. By the way, guys, everything actually here has been discussed before. Through our previous classes, I discussed many aspects, many points. So you will feel like there is nothing new because you already have discussed this before. You have seen some kind of this discussion, but here we have to make it in a formal form to make it like a theory of how to make things parallel in manual mode or in automatic mode. Okay, so automatic and manual parallelization. Here we have designing and developing parallel programs has characteristically been a very manual process. So the first point that the parallelization of programs mostly is manual process. Mostly is a manual process. So this is the responsibility of the programmer to decide what things to work in parallel and what things to work in serial or in sequential. Okay, so the programmer is responsible to define exactly similar to what we have done using the example of last week in C#. We define the thread, then we start the thread, we pass the data to the thread, how to kill the thread, everything is our responsibility as programmers. Okay, so the programmer is typically responsible for both identifying and actually implementing parallelism. So you have to define what parts could work in parallel and how to implement them. This is your responsibility as a programmer. Very often, manually developing parallel codes is a time-consuming, complex, error-prone, and iterative process. So this is the characteristics of developing parallel codes. Actually, especially if you use one of the traditional programming languages like C or C++, sorry, not C, maybe Objective-C, maybe C++, Java. This has a lot of things that you have to work around because the parallelization, actually the multi-threading programming in this kind of traditional programming languages is a little bit harder than the modern languages like C#. So C# is more clean, more clear also at the same time. So the way of calling the thread or initiating the thread is straightforward. Everything is simple. Okay, so it's not that simple compared to the procedural programming, but somehow simple compared to the other traditional programming languages. So Anyway, it consumes time because you have to think here in parallel. When we build the sequential programs, we only think sequential. So tasks are one after another and easy like that. But when we think to make things work in parallel, to improve the time, to reduce the processing time, to increase the speed and so on, then we have to think how are the functions that could work in parallel, and how we could pass the data between or among the threads, and how we can start the thread, how we follow the thread, how to kill the thread, how to make this thread waiting for the other, how to look our variables and so on. A lot of stuff we need to understand. So the thing is time consuming and complex a little bit compared to the normal or to the traditional programming. And also it could have a lot of errors. So every time you need to compile, you need to check, then you find some bugs, some errors, then you have to go back, fix them, run again, check again, maybe another problems happen. Yeah, like that. The process is not that easy compared to the traditional way of programming. Okay. So for a number of years now, various tools have been available to assist the programmer with converting serial programs into parallel programs. Okay, so there is some tools that helps you to put your program, the sequential program, you give it to that tool, then that tool try to make it parallel without you concerning about everything, about threads, about controlling the access of shared memory and so on. So you don't need to do that. But the problem is the problem of these tools actually is that they are not perfect. They are not perfect. And the most common type of tool used to automatically parallelize a serial program is parallelizing compiler or preprocessor. But this tool actually is, as I said, is not perfect, is not working as you intended, or as it was intended, but it tries its best to make it parallel. So the tool will find the places where the parallelism could be applied, and especially if there is loops or maybe other parts that are very independent from others, then they can run it in parallel. Otherwise, if the program is very complicated, serial and very complicated, then sometimes these tools cannot do anything, cannot make it parallel. Okay, so in this case, it will fail, totally fail. So it will run the software or the program as sequential after it wastes your time to try make the serial program parallel, but after that it will fail, then will run the program as serial as before. So it could also provide some extra overhead that's unnecessarily consumed. Okay. Yes. Parallelizing compiler, this is one of the tools actually that makes the serial programs parallel. So parallelized compiler generally works in two different ways. So the first way is fully automatic. So the programmer doesn't need to mention what kind of or what part of the code is need to be run in parallel, or what function need to be run in parallel. It doesn't mention anything, the programmer. Okay. So that's why they call it fully automatic. We take the serial, normal or usual serial program, we give it to the parallelizing compiler, then the parallelizing compiler will run in the fully automatic mode. Then it will try to analyze the source code and identify the opportunities for parallelism. So if it found some opportunities or some parts of that code that could run independently in parallel, then it will apply parallelism on that. Otherwise, it will keep it serial as before. So the analysis includes identifying inhibitors to parallelism and possibly a cost weighting on whether or not the parallelism would actually improve performance. So this is the one of the major problems. So here the compiler, the parallelizing compiler, will try to identify inhibitors to parallelism, and if it's possible to I mean to improve the performance or not. But sometimes the output of these tools will not be satisfactory. Okay, so here the main points that this kind of tools try to play on is the loops, like do, for loops are the most frequent target for automatic parallelization. So mostly these loops will be parallelized. Even though if that loops are not responsible for any bottleneck or any delay. Sometimes those loops are not that big issue, not that hotspot of the program actually, but these tools will try to make it parallel. Sometimes it will introduce a lot of unnecessary overhead. Okay, is that clear, guys?
Yes, doctor.
Yes. Okay, the second mode or the second way is the programmer directed. So programmer directed here, the programmer will use some compiler directives. So there will be some keywords that the programmer have to put in front of some places, like in front of function or inside the loop or whatever, then as a flags actually for the compiler to tell the compiler that this area could be parallelized. So this is what they call it semi-automatic. So the programmer doesn't need to do the entire work of the parallelization, but it need to apply only some directives, only to write some keywords inside the code to mention where is the parts of the parallel. Okay. The programmer explicitly tells the compiler how to parallelize the code. So only the programmer need to use these directives to mention where is the places that could run in parallel. This one may be able to be used in conjunction with some degree of automatic parallelization also. Yes, because as I said, this also called semi-automatic, not fully automatic. So in this case, the programmer need to mention using some directives where is the parts that could run in parallel. Then after that, the parallelizing compiler will run the automatically to make things run in parallel. Okay, so some part is manual, which is the responsibility of the programmer to use these directives. Then the other part is automatic, which will be done by the parallelizing compiler. Okay. So if you are beginning with an existing serial code and have time or budget constraints, then automatic parallelization may be the answer. So it's maybe better to use automatic parallelization. If you don't have time, if you don't have budget to make it parallel. So in that case, you could use the automatic parallelization, which is more faster, more cheaper. Okay. Otherwise, you have to spend a lot of time or a long time to parallelize the code, and that will need budget to accomplish that. Okay. So, however, there are several important caveats that apply to automatic parallelization, such as wrong result may be produced. Okay, so wrong result could be produced. Okay, let us make it could be produced. Performance may actually be degraded. So if the nature of the program actually is not parallelizable, so if the program cannot be parallelizable by nature, then this automatic parallelization will waste time trying to make it parallel, then it will fail, and after that the program will run in serial, then we waste our time and we introduce extra unnecessary overhead. Okay? Also, sometimes serial application or maybe a small problem that's solved by a certain program which is given to the automatic parallelization tool, then the tool will make it parallel. So it will introduce like synchronization, communication, multi-threadings, and everything for that small problem. Then we will see that the serial program is faster than the parallel. In this case, why? Because if the problem is very small, actually there is no point to make it parallel. That's why if we try to make small problems parallel, then we will see that the performance is going to be degraded. Why? Because we will introduce an extra overhead for the communication, for the synchronization, and for trading, and so on, which will make things more slower. Okay? Here, much less flexible than manual parallelization. So here, when we use the fully automatic parallelization, we don't have much to do, actually. We don't have much to tell that automatic parallelization tool what to do. We cannot tell anything. Okay, we only have some directives that we could use. That's all. We cannot fully control the process or how to parallelize the thing. And also we cannot guarantee that the same program, if we run the same program on different parallelization tools, we cannot guarantee the same performance. Why? Because every tool is running in different way. Every tool is analyzing the code in different way, right? So that's why it's not in our hand, actually. The control is not in our hand. And also it's not flexible compared to the manual parallelization. Manual parallelization is time consuming, need a budget, but also at the same time is guaranteed. And the second time is controllable. Third thing is flexible. Fourth thing is we make it as we need it, as we wanted it to be. So we know how it will work, and we know the way, is it wrong way or correct way. We know what is the hotspots of the program, where is the bottlenecks, so what parts that need to be parallelized. But in automatic, we doesn't know. So the compiler will do everything on behalf of ours. Okay? Limited to a subset, mostly loops. So not all parts of programs will be parallelized. Normally, it's only limited to loops. Okay? Loops or subsets of code, not everything in the code. So may actually not parallelize code. So the code, not every code could be parallelized by this automatic tools. So if the analysis suggested there are inhibitors or the code is too complex, then the program will not be parallelized. Okay? Is that clear, guys?
Yes, sir.
So far, yeah. Actually, I have explained this before, guys. That's why maybe you feel like, okay, this thing is not new, right? You feel like familiar with this, because many times we explain this, sometimes explicitly, sometimes implicitly, but we have gone through this before. So the only new thing is the automatic tool here. I think you never heard about it. This is the new topic for today. But for the other things, we already know about it. Okay, most automatic parallelization tools are designed for Fortran, most of them. So maybe in the last decade, there is some tools are designed for other programming languages, but actually not very famous. The mostly programmers are tending to make it manual, to parallelize their programs manually, especially for programs that's designed for heavy work, for industrial work, and so on. So it must be carefully designed, must be carefully parallelized. Okay. The remainder of this section applies to the manual method of developing parallel codes. So from here onward, we will not talk about the automatic. So everything's supposed to be on the manual process of building parallel programs. So here, understand the problem and the program. Guys, this one actually I have explained in many classes. I have explained in many classes that not all problems could be parallelized. So the thing that we have to understand at first, before we start designing or before we start writing the code or before we start thinking about how to parallelize, is the nature of the program. So we have to understand the nature of the program. If there is independent parts of the program or independent functions that could be run concurrently, then we should think about how to make it parallel, if that makes a benefit to the organization or to the customer. But if, let's say, if the customer does not care about the time or when the function finish or when is the processing finish or how long it takes, if they don't care, there is no point to make it parallel. Okay, because parallelizing is very costly. Okay, when we need to parallelize, when we work some things related to real-time applications or real-time problems like fire detection system or something like that, that's very critical. So in that case, we have to make things faster. We have to make things faster. Okay, we have to make things parallel. Why? Because the events could happen in parallel. By the nature of the what they call it, the fire detection system, the events could happen in parallel. So maybe a smoke happen in one place, maybe the temperature is detected by another sensor. So every sensor need to be in different thread. Otherwise, if the program is serial, then the performance or the detection of the fire maybe will be slow. So maybe the fire happened and we detect it after 1 minute or 2 minutes, which is very late sometimes. So what we need to do is to make the program as fast as we can, as fast as possible. Okay. But what if the nature of the program is sequential? Is it here feasible to make it parallel? Definitely no. Why? Because this is going to waste our time. It's going to waste our time. Even if we try to make it parallel, it's going to waste the resources. It's going to introduce a lot of overhead, and the program finally will run in a very bad situation compared to the normal sequential program. Why? Because the nature of the problem that we are trying to solve is sequential, not parallel. Okay? Okay, undoubtedly, the first step in developing parallel software is to first understand the problem nature that you wish to solve in parallel. The problem nature that you wish to solve in parallel. So if the problem nature could be solved in parallel, then we go ahead. Otherwise, if the problem nature cannot be in parallel, cannot be solved in parallel, because the nature of the problem is sequential, then we have no point to think about parallelization. It's wasting our time, actually. So that's why we need to forget about the parallel sometimes. Okay? If you are starting with a serial program, so for example, if let's say you have an existing program that solves a certain problem, then you was asked by the management or by the customer to check that program and change it to parallel. So in that case, it's very necessary to understand the existing code first. Very necessary. You have to understand how the existing code works. Then after that, you try to find where is the bottlenecks, where is the hotspots, where is the independent functions, to know where to play your parallelism. Okay, where to apply or where to put your parallelism, where to focus. Actually, you have to find where to focus. Where is the bottlenecks? Where is the points of flaws? Okay, that makes the serial or sequential program very slow, for example. Okay, so before spending time in an attempt to develop parallel solution for a problem, determine whether or not the problem is one that can actually be parallelized. This is to summarize, actually. This is what I was telling you from the beginning. So before you spend your time to make solve a problem in parallel, just make sure that the problem is parallelized. If not parallelized, don't waste your time. Okay, guys? Is that clear?
Yes, doctor.
Hopefully. Okay. Now we have an example of parallelizable program. Okay. Here, this parallelized problem, actually, the problem that could be solved in parallel. What does it mean? What does it mean that problem could be solved in parallel? That means the problem could have some independent parts that could be run concurrently at the same time to solve the problem. Okay, so here, calculate the potential energy for each of several thousand independent conformations of molecule. Okay, so I know this thing is out of the computer science area, but anyhow, I tried to make it easy for you. So instead of this example, we could think that the molecular here is independent, similar to matrix item. So all of you knows how to deal with matrix, right? So maybe addition of matrix, summation of matrix, maybe subtraction of matrix, multiplication of matrix, division of matrix. Everybody knows how to make that, right? So by nature, all of that operations could be solved in parallel. Why? Because all items in the matrix are independent, right? All items in the matrix are independent. That's why it could be solved in parallel. So this problem is able to be solved in parallel. Each of the molecular conformations is independently determinable. So as you can see here, from the beginning, they say to calculate the potential energy for each of several thousand independent. Here, from the beginning, we have a clue. We had a clue about how things could be, right? So from here, we could start. Okay, this is a good sign. This is a good sign that let us dig deeply to understand more about the nature of the program or the nature of the problem to see whether it could be parallelized or not. Okay, so each of the molecular conformations is independently determinable. Okay, this is very good sign. So if each item or each molecular conformation is independently determinable, that means we can independently calculate the molecular conformations concurrently. Okay, so the calculation of the minimum energy conformation is also a parallelizable problem. So this problem actually is parallelizable. Okay? Is that clear, guys?
Yes, Doctor.
If you remember last time, I explained about this when we take the example of matrices and how to multiply matrices and how to take, how to divide or how to partition the work into some tasks. So maybe the first task will take the first row, multiply it to the first column in the second of the second matrix. Okay, sorry guys. So that's example. So maybe the second task in that example will take the second row from the of the first matrix, multiply it by the second column of the second matrix, right? And those operations could be run concurrently on the same time, right? So the second task doesn't need to wait for the first task to finish, because both of them are independent. They can run from the first time, from the time zero, independently. And each row and column could bring the result. Then after that, the results of every task will be combined together by the main thread to give the result or the final result. Okay, let us come here and see one of the non-parallelizable problems example. Okay, so this is very common actually, very common example. So the calculation of the Fibonacci series. So Fibonacci series is very common example when we talk about parallelization. Why? Because this problem actually cannot be parallelized. By nature, it's sequential. So in order to calculate the second item, we have to calculate the first item before that. And when we need to calculate the third item of the series, we need to calculate the second and the first before that. Okay? Let me explain this. I don't know. Do you know what's the Fibonacci series? Anyone of you knows what is that? I don't think. Okay. Fibonacci series is like this. It starts with 0, 0, 1. So 0 and 1 is not calculated actually. Then after that here there is 0 missed. So 0, 1, 1, 2, 3, 5, 8, 13, 21. So what does it mean? For the first and second items, they are not under the equation. So this series actually is calculated from the third item onward. So the third item, this one, equals the result of first and second. So 0 plus 1 is 1. Okay, this item actually equals the result of 1 plus 1. This item is equals to the result of 1 plus 2. So in order to calculate any item, you need to calculate the two previous items. Okay? Two previous items that comes before that. So that's why we cannot calculate this unless we calculate this and this. And also to calculate this, we have to calculate this and that, right? So that's why the problem is serial, is sequential. There's no point to make it parallel because it will never introduce any improvement. The opposite way, it will make things more worse if you try to make it parallel. Okay? Everyone knows how to calculate or what's the Fibonacci series? Is that clear?
Clear, Doctor.
Yeah. Okay, let us see what's the formula here. The formula here, actually, this one is not k plus 2, actually. This one is kn. It's supposed to be kn. Yeah, this one is supposed to be kn. This one is supposed to be kn plus 1. and this one supposed to be kn plus 2. Okay, what does it mean? This if k actually, for example, is this. K plus 1 means this item. So this item, which is the fk, and this item, which is the fk plus 1, when we sum them together, we will get the result of the third item, which is k plus 2. Okay, is that clear, guys? Don't confuse yourself. Actually, the presentation of this is not that good. So maybe if you go to anywhere, so Fibonacci Series. Okay, try to find yeah, okay, this is a very nice website. Math is fun. Anything related to math you want to understand, if you find it in this website, it will be presented in a very simple way. So if you go here, you can see, okay, 0 1 1 2 3 5 8 13 21 and so on. Okay, here the Fibonacci sequence is the series of numbers like this. The next number is found by adding up the two numbers before it. As simple as that. The 2 is found by adding the two numbers before it, which is 1 plus 1. The 3 is found by adding the two numbers before it, 1 and 2. For this 5, it will be the addition of the two numbers before it. For 8, it's supposed to be equal to 3 plus 5. 13 is equal to 8 plus 5. 21 is equal to 8 plus 13. 43 is equal to 13 plus 21, and so on. Okay, is that clear? Very simple, guys. Okay, so the next item after 34 is supposed to be 21 plus 34, which is 55. Then after that, it's supposed to be 89, and so on. Okay, as you can see, 55, 89, 144, and so on. Makes a spiral. So this thing actually, if you apply or if you draw this function, it will result in a spiral. Actually, it will show you a line that's similar to a spiral. Okay, when we make squares with those widths, we get a nice spiral. Okay, so do we see how the squares fit neatly together? For example, 5 and 8 makes 13, 8 and 13 makes 21, and so on. So this is out of the scope of our course. So the only point that we need to know is this: how to calculate the things. So here we have n and xn. For these two items, it doesn't apply. That equation does not apply. Where is it? The equation in this equation. This equation does not apply for the first and second item. It will start from the third item, then the third item will equal the first and second, fourth item will equal the second and third, fifth will be equal the summation of third and fourth, and so on, as you can see here. Okay? If you need more information, you can go through it and find what you need. So this is the meaning of that equation. Okay, this is a non-parallelizable problem because the calculation of the Fibonacci sequence as shown would entail dependent calculation. Dependent calculation. Why? Because the third is dependent on the first and second. The fourth is dependent on the second and third. So that's why we cannot calculate it in parallel. So if we parallelize, for example, if we make task that calculated this time in separated thread, and another task to calculate this item in separated thread, then if we run the threads in parallel, all thread will be waiting for the previous one, right? Then finally they will run in sequential. So there is no point. So we will waste our memory, we will waste our time to do to build the parallel program, and also the processors will be all the time waiting, so the resources will be wasted. Okay. Okay, as shown, would entail dependent calculations rather than independent ones. Okay, so the calculation of the k plus 2 value uses those of both k plus 1 and k. These three terms cannot be calculated independently and therefore not in parallel. Okay, this is one of the very famous examples of non-parallelizable problems. Is there any question, guys?
No, doctor. No, doctor, so far.
Are you sure? All of you doesn't have any question? How many one is attending our class? 30. Okay. Okay. Let us continue here to this slide. So identifying the program's hotspot. Okay. Now here, if you remember at the beginning, to make things parallel, we have to understand, right? We have to understand the problem and the nature of the problem. So we try to understand if the problem is parallelizable or non-parallelizable. So if the problem non-parallelizable, then we stop thinking about how to make it parallel. If the problem is parallelizable, then the second step is to find where is the hotspots of the program. Where are the hotspots of the program? What does it mean, hotspots of the program? It does mean the critical points or the main points that makes a lot of delay, for example, or had a lot of complexity, for example, or whatever. So those hotspots supposed to be solved or parallelized in order to reduce the time, processing time, and also to reduce the cost, also to reduce the waiting time, and so on. So know where most of the real work is being done. So try to find where is the most real work in the program. So you try to find the major functions that wastes a lot of time because it's running in sequential. Okay, so the majority of scientific and technical programs usually accomplish most of their work in few places. Yeah, sometimes you have, for example, three functions x, y, and z. X is only to calculate, for example, square root, for example, and y is calculating a lot of stuff, maybe multiplication of arrays or whatever. Then function y is also very simple to do summation for two numbers, for example. So the main point is to don't think about the x and about the z function. Why? Because both of them are very small, and there is no point to make them parallel. So the focus will be on the function that wastes a lot of time. Okay, maybe I need to draw this to let you realize. So for example, if let's say we have function 1, which is sum of a and b, okay? Then function 2, which is multiplication of matrix 1 and matrix 2, for example. Okay. Then, for example, we have another function that calculates function that subtracts a from b, for example. So in this case, 3, which is very simple, actually, very simple. 1 and 3 are very simple functions. So why we do subtract a and b, for example? Do we need to waste time to make this parallel, guys?
No.
Because this one is very easy, right? Very simple. It has no complexity. It doesn't waste time, actually. Okay. Do we need to do this to make this parallel also?
No.
Also no. But what's about this?
Parallel.
Yeah, this need to be run in parallel. So this means this function is a hotspot here. So we have to find where is the hotspots. Then we try to make them run in parallel or to solve them in parallel. Okay? So this is the meaning of the this slide. So profilers and performance analysis tools can help here. In order to know where is the hotspots, sometimes is not easy, especially if the application is very complicated. So in that case, you need to use some profilers or performance analysis tools to find where is the hotspots or where is the functions that take time. Because the profilers could tell you how long the function X takes and how long function Y takes, how long function Z takes. Every time you run, you could see it in the profiler. Okay, there are a lot of profilers related to many technologies, many softwares, many applications. There's some profilers related to network, some profilers related to database, some profilers related to applications. So you can find whatever you need, then you can use them. Okay. Focus in parallel. Actually, I want to comment about this. Honestly, to make things run in parallel or to build or design parallel applications actually is not easy. It's not easy way for the designer, for the system architect, is not an easy way. So it's a long process. It needs a lot of team of programmers, and also it would take long time to understand, to realize where's the hotspots, where's the bottlenecks, and where you have to improve the speed, where you have to make things parallel. Yeah, so this actually needs a lot of experience. It's not an easy task to use a profiler like that, or maybe analysis tool, and easily in 1 or 2 minutes you can find the hotspots like that, and everything is nice like a heaven. No, this is not a realistic scenario. So in real life, normally customers or organizations who ask for programmers to be parallelized are the very big companies that has a lot of work. Their work is real time. Their work is critical. The minute or the second is cost, actually. So that's why it's not easy to do so. Okay, it's not easy to do so. It's not easy to do it by yourself, only one person, and also it doesn't take a short time. It's not easy to analyze the things and understand it and diagram the things and design and architecture is not easy. Not impossible, but also not easy task. Yeah, for project like maybe you do encryption project for your final year project or something like that, you can do it. One person can do it, easy. But for big projects, it doesn't work. So you have to be in a team, and the team have to have very good experience on this, and you have to have tools in hand, skills in hand, a lot of things. Okay? but this actually a source of money, actually, very good source of money. If you want to look for a very good source of money generation, then you try to improve your skills in here. Okay, guys? And the last point here, focus on parallelizing the hotspots and ignore those sections of the program that account for little CPU users. So let us come back here. So in this, or the last point here, means that you find where is the major functions in your application, then try to focus on them. So don't waste your time here in function 1, don't waste your time in function 3. So you need to focus on only function 2, okay? And also you need to focus on the frequently used functions. Frequently used functions. So the rarely used functions, there is no point to make them in parallel. Because unless they are rarely used, but they are major. For example, when you run it monthly, some functions are monthly calculated, like calculating the salary for the university staff, for example. So let's say that the university has 1,400 staff, then you one time click the button of calculating the salary, then it takes 2-3 days, for example. Here, this is a hotspot. Event to the function is very rarely calculated or very rarely called, but it's a major function. It's a hotspot. That's why we need to focus on that. And instead of waiting for 3 months to get the salary ready for the staff, then we try to make it parallel, maybe to finish in 1 day or maybe in half day or something like that. Everybody will be happy later if we do so. Okay. Identify bottlenecks in the program. I already explained this, but anyway, I'm going to go through it again. So are there areas that are disproportionately slow? So you try to find where is the areas that are very slow, or where's the functions or commands that are very slow, then you try to make it parallel if they are parallelizable. If they are non-parallelizable, then you have no option. You have to wait. So the only thing to improve that unparallelizable functions, to bring faster machine, to run them on faster machine. So maybe if let's say your processor speed is, for example, 1,200 megahertz. So maybe you need to bring like 3,000 megahertz, for example, to make it faster. Okay, this is what you can do only, because the problem is non-parallelizable, but it's very slow. So in this case, we have to not focus on how to parallel the program, but we need to focus on how to bring faster hardware, because this is the only option that we have in hand. Okay, so are there areas that are disproportionately slow or cause parallelizable work to halt or to be deferred? So for example, if let's say you have I/O actually is when you deal with the hardware, like when you deal with the camera, for example, to take a picture, or you deal with the fingerprint device to take a fingerprint of customer in bank, for example, or maybe to deal with the hard disk to save data, or maybe to deal with the audio device to record something. So that are points of the I/O use. Normally, when we deal with the hardware, with the I/O, especially the I/O, these points of the program will be hotspots, will be bottlenecks, will be slow points of the program. So that's why we need always to try to find where are the I/O points of the program. Then we try to understand the nature of their use. If it's parallelizable, then we try to make it parallel. That will improve a lot of things in our program. Okay, may be possible to restructure the program or use a different algorithm to reduce or eliminate unnecessary slow area. So this is only a suggestion. So it's a very common point. So maybe if you restructure the program, then you will improve the performance, or maybe you try to find, for example, if let's say you do encryption, maybe you are using Bluefish encryption algorithm, then you find it very time wasting, then you try to go and use, for example, skipjack or SHA or whatever, which is more faster. So this is only suggested solutions that could work. Okay, but definitely it have to be to fulfill the requirements of the organization or the customer. So if let's say the customer wants you to use Bluefish, then you don't have any option to change it. For example, if for example you are doing encryption, for example. So if the requirement is to use Bluefish algorithm to do encryption, then you have no choice to change it. If you change it, for example, to SHA or maybe to skipjack or maybe whatever, then the customer or the organization will not be satisfied, right? So some things have to fulfill or to obey the rules and the regulation and the needs, the requirements of the organization and the customer, even if they are very slow, unless the requirements allow to change. Okay. Other considerations here: identify inhibitors to parallelism. One common class actually is one common class of inhibitors. Oops. One common class of inhibitors is data dependence. So you have to find if the data dependent on each other, like what happened in Fibonacci sequence, that means there is no point, right? There is no point, because the dependency of data on each other will not allow you to make things parallel. So this is what they call it inhibitors. So in this case, the dependency of data is the inhibitor. Okay. Investigate other algorithms if possible. So if there is any other function that could give us the same Fibonacci sequence with the different way of calculation, then we can use it, better than using the dependent way. Okay, but if there is no other option, then we have nothing to do. So this may be the single most important consideration when designing a parallel application. So this is very important consideration to think about the inhibitors, or to understand the nature of the problem before you start thinking about how to design the parallel application. Okay, otherwise you may waste your time, you may waste the time of the organization, you may waste the money. And if you do so in a real life, for example, if let's say you are hired in a company, then you show off, you try to make you told them that your program could be changed to parallel and the performance will be improved and so on. Then the organization or maybe your boss become very happy. Then he supports you. He pay 10,000 ringgit to make that. He hire some new staff to help you in the team to make the application parallel. Then after that you fail. Why? Because the nature of the problem, you come after 30 days, maybe after you waste 10,000 ringgit, for example, then you came to your boss and you say, boss, I want to tell you something. And he say, okay, what? You say, unfortunately, the problem that your application solves is by nature sequential. That's why we cannot make it parallel. Do you know what will happen in this case? You will be fired. You understand? You will be fired from your job if this happens. So that's why you have to think twice before you say anything in this regard. Okay, you have to think twice before you waste your time. You have to think twice before you waste the resources of your organization. Okay, otherwise bad things could happen. Okay, now we come to partitioning. So we come only to partitioning if the things or the problem is parallelizable. If non-parallelizable, then we will never come here. Okay, so partitioning is a second or third step towards parallelization. So the first step to understand the nature of the problem, the second step to find the hotspots and bottlenecks, the third thing is to make partitioning, is to make decompose the program or the data into small partitions. Okay, so that small partitions or small chunks of data or small chunks of functionalities supposed to be independent from each other. Supposed to be independent from each other. So the coupling here, if let's say this is the function the functions of our program. So here what we have is task 1, task 2, task 3, right? So here this is function 1, this is function 2 or task 2, and this is task 3. So here, is there any information need to be passed from function 1 to function 2? No, right? So this is here between function 1 and function 2, there is no relation. There is zero coupling, actually. There is no coupling between the two tasks or the two functions. Okay, is there any data needed to be passed from first and from the second and third? There is no, right? Also here there is no coupling between 2 and 3. But if let's say in order to do multiplication of matrices, so in every matrix, from every matrix we have to take the first row, then of the first matrix, the first column of the second matrix, then after that we take item by item, right? So we take the item 1 from the first row, multiply it by the first item of the first column from the second matrix. Then what we need to have is to have function 4 that could multiply like this, A and B. Okay, so sorry. Okay, Z, Control Z, function for multiplication or multiply A and B, for example. Okay. A and B are parameters here, guys, okay? They are not the same value, not the same data. They are only names of parameters, okay? That's why there is no relation between all functions. So in this case, if we want to do multiplication of matrices, so to multiply the matrices, we need to go through rows, columns, and in each row and column, we need to select items. Then we send them to the multiplication function to multiply them and get the result. So in this case here, we have function 4 here. Then this function actually is always waiting for the this function 2 is always waiting for the result of function 4. So there is a relation here. There is a relation between 2 and 4, but this relation is very loosely. Why? Because here the multiplication, it does not take long time. That's why the second function does not need to wait too much for the function 4 to get the result, to multiply two items, right? That's why it's not going to be considered as a tightly coupled, because here we have tightly and loosely. We have tight coupling and loose coupling. Okay, if tightly coupling, then we have to have our threads waiting for each other, and we still have a kind of serialization in our application. Some problems are like that, actually. Some problems has some parts where we can run things in parallel, but in some places things have to be in serial. Exactly as if you remember in the last week, I will open the code and show you how this could happen. Okay. Okay. So here, this is our last factorial sum, or what? Oh, not that. This one. Oops. I don't know, where is it? Oh, I changed the name of the folder. Anyway, let us open a local folder and see. Okay, courses distributed and parallel, examples of code. Then I don't know which one. I think this one is the factorial, right? Oops, no. Okay, let us see this. Select factorial, and see how. Actually, my Visual Studio is a little bit slow because I since about 4 or 5 years I did not making fresh installation. I update from version to another, update from version to another until it become very slow. That's why I need to uninstall everything, then I freshly install again. Okay, guys. In this program here, we have the factorial function that could work in different threads, right? So we could have multiple copies of that function and run them in different threads, thread 1, thread 2, thread 3, thread 4, and so on. So in this case, the initialization of the threads here is sequential. Could we make this parallel? The initialization of the threads, could we make it parallel? Anyone could answer? Could we make this part, the initialization of the threads, could we make it parallel?
Yes.
No. Cannot make it parallel. Why? Because this one is the start point, and the start point of any application must be sequential. Must be sequential. There is no 100% program that's there is no program that's 100% sequential. Parallel. 100% parallel. It never happened. There at least will be a starting point that run in sequential mode, because parallelization need to be initialized, and the initialization must be sequential like this. We cannot do anything other than that. So in this case, we cannot say that the program is sequential here. Why? Because here we have multi-threads, and every thread could calculate its factorial and so on. Then the time could be cut to the quarter, or maybe to the half, compared to the sequential. So that's why we cannot say this program is sequential. Why? Because it's parallel. It's parallel. It's correct that the initialization point is still sequential, but this is the nature of all programs, the nature of all parallel programs. Okay? Okay, I will give you a real example. I'll give you a real example. If, let's say, you have four sandwiches, guys, and you have four friends, and you are going to give each friend one sandwich, and you ask the friend to eat it until it finishes. So if you give the first sandwich to the first friend, then you wait until that friend eat the sandwich and finish it to give the second sandwich to the other friend after that. In this case, it's sequential, right? Fully sequential. So the second friend will wait until the first friend finish his sandwich to get the sandwich and start eating. And the third also need to wait for the first and second, right? So in this case, the whole program is serial or sequential. But what if you give them sandwiches at the same time and you tell them to start eating at the same time? Are you with me, guys? So what will happen here in this case? This program or this scenario is parallel, right? Because every friend could start eating at the same time, and they could finish their sandwiches at the same time, or maybe very near time to each other, right or not?
Yes.
Yes. But okay, let us think about it. If how we give the sandwiches to the friends to start eating. If you want to give to hand sandwiches to each of them, so you definitely will give the first sandwich to someone, right? Maybe the first friend, maybe the second, maybe the third, right? Then you will give the second to the other one, third, fourth, right? So the starting point of assigning tasks here or giving sandwiches to the friends is still sequential. Maybe you will say that we can put sandwiches on the table and we ask them take it at the same time. We still have a sequential here. Why? Because we still need to start to bring sandwiches, to set them on or to put them on the table in some way. Then after that, we have to give a trigger to the friends to take their tasks or to take their sandwiches, right? And at that moment, when we trigger or when we ask friends to take their sandwiches, there could be one is faster than the other. It could happen, right? So in that time, if let's say the third friend is faster than all of them, he will pick his sandwich first, then another one will pick after him, maybe by a slice of time, something like that. It's still sequential, guys. Still a sequential point of initiation. So here, the initialization of the threads or the initialization of parallel program is always sequential, guys. Always sequential. Okay? Is that clear?
Yes.
Yes, sir.
Yes, doctor.
Okay, good, good. That sounds good. Okay, partitioning. What is the partitioning? The partitioning actually is one of the first steps in designing a parallel program. So that first step is to break the program into discrete chunks. What does it mean, discrete, guys? What does it mean? Do you know what does it mean, discrete? Anyone knows what is the meaning of discrete?
Individually separate.
Discrete in Bahasa Melayu. What is the meaning of discrete? I will try to explain. It's also discrete, guys. Discrete means it's separated tasks. So here, what we need to do is to break the problem into separated parts. That parts, we try to make them independent as much as we can. We try to make them independent as much as we can. Okay. Also, if they are related to each other in some way, we try to make that relation as loosely as we can. We try to loosen the relation between the chunks. Okay. So here, what we need first is to break the problem into discrete chunks or functions of work that could be distributed to multiple tasks and could be run in parallel or concurrently at the same time. This is known as decomposition or partitioning. Okay, the same meaning. Decomposition, partitioning is the same meaning. Okay. Also, breaking the problem into discrete chunks is also means decomposition. Okay. There are two basic ways to partition computational work among parallel tasks. So there are two ways to do partition, right? So the first way is based on the domain, which is called domain decomposition. The second way is based on the function, which is called functional decomposition. Okay. Okay, I will give you some example. So maybe you have a system that calculates the salaries for university staff. So maybe if you want to decompose the system or break the system into discrete chunks based on the domain, so in this case you can say that let us separate the academic from the non-academic. So you calculate for the academic in one thread, and you calculate for the non-academic staff in different thread. So this is the separation or the partitioning based on the domain, right? The second thing is based on the function. Based on the function. So based on the function, you can say like, let us calculate taxes first. Then after that, let us calculate the what they call it allowances. After that in different thread, and after that we may calculate or combine things together in different thread. So this is based on the function. Is that clear, guys?
Yes, doctor.
Yeah, okay, good. Okay, what do we have in these slides actually is very general. What I have explained to you is more detailed compared to these slides. So you're supposed to easily understand, and we're supposed to easily go through these slides without wasting time. Okay, guys? If you have any question, please stop me. If you have any question, don't let me go until you understand. Okay? So here, domain decomposition or decomposition based on the domain. In this type of partitioning, the data associated with a problem is decomposed. So in this case, we try to separate or to divide the data based on the problem. So for example, for the academic staff, we put their data as a one chunk for the academic staff. So we separate the academic staff data and we make it as one chunk. Then we separate the non-academic staff data and we make it as another chunk of data. Then the first program will solve the academic, or will calculate the academic salary. The second program will calculate the non-academic salary based on their data. So the data is independent, the programs are independent. Okay, or maybe the threads are independent. So each parallel task then works on a portion of the data. Okay, so every task, the task that calculates the academic will run on its data, and the task that will calculate the non-academic salaries will work on its data independently. So they can work at the same time, they can work concurrently in parallel. Okay, so this is what they call it, decomposition based on the domain. So here in this slide, there's nothing to explain, because this one is kind of playing with puzzle. They try to tell you that you can partition your data in any direction and whatever. I don't care about this, because I already explained in deep details. Okay, so here you can break it. Based on the rows, based on the columns, based on the rows and columns at the same time, or whatever. It's possible. Depends on the nature of the program or the nature of the problem. There are different ways to partition data, as you can see here. Then functional decomposition. So this is the decomposition based on function. So in this approach, the focus is on the computation that is to be performed rather than on the data manipulated by the computation. So if you remember, in the first example, when we say academic and non-academic, actually calculating the salary actually will use the same function, right? For academic and non-academic, they will still need to calculate the tax in the same way, right? They still will calculate the allowances in the same way. But they will use this function, the same function, on different data. So in this case, we have single instruction, multi-data, right? That's why the decomposition is based on the domain here. So the function will be two copies of the same function will run on different data at the same time. But in this case, if let's say we have multiple functions, that could run on the same data, for example, if let's say we don't have non-academic and academic, let us call them all staff, and all staff are the same. We don't want to differentiate between them, and we want to calculate based on the, for example, staff ID. We don't care about whether this staff is academic or non-academic. So in this case, what we need to do is to make sure that we have multiple functions that are separated from each other and can work independently. For example, the calculation of tax and the calculation of allowance of the staff, of the same staff. So in this case, we have multiple functions and multiple data, right? So if multiple functions and multiple data, the first function is the tax function, the second function is the allowance function, the third function is the final salary calculation. So in this case, we can make decomposition based on the functions. So we can take the function of tax, we put it in different thread, so that function will calculate all taxes for all staff. For each staff, it will be calculated under that thread. And also at the same time, there is another thread will calculate the allowances for each staff. Then after that, there is another thread that calculates the final salary based on the result of the tax function and the result of the allowance function for each staff. So in this case, we have separation or decomposition based on the function. Is that clear, guys? Is that clear?
Yes, sir.
Okay, good. So the problem is decomposed according to the work that must be done. Yes, the work that must be done in the first case, in the first function here, is to calculate the tax, right? And the work that must be done in the second task is to calculate the allowance. And the work that must be done in the third task is to calculate the final salary, right? Like that. So each task then performs a portion of the overall work. So each task will run its own functionality on all available stuff for each available stuff in the database. Okay? Then, so the separation here is not done based on the domain, so we don't separate or decompose the stuff into two groups like academic and non-academic here. So we just calculate the task for each stuff in one task. We calculate the tax. And also we calculate the allowances for each stuff in the task 2. Okay? And the main program will calculate all of that, will aggregate all of that results from different tasks and combine them together to calculate the salary of each staff in the database. Okay? Functional decomposition lends itself well to problems that can be split into different tasks. For example, economy systems or ecosystem modeling, signal processing, climate modeling, and so on. Okay? There are too many examples of problems that could be classified under functional decomposition or could be solved based on the functional decomposition. Okay, let us come to the ecosystem modeling. So each program calculates the population of a given group. Okay, so where each group growth depends on that of its neighbors. Okay, as time progresses, each process calculates its current state, then exchanges information with the neighbor population. All tasks then progress to calculate the state at the next time step. So in this case here, what we have to do, we have to calculate many things for many types of what they call it of groups here. So maybe plants, what they call it herbivores or whatever, or carnivores, I don't know how to read them, all of that stuff. Actually English is not my mother language, that's why it's very hard to me also to read this. Guys, anyway, there are many groups of things here that we want to calculate or to do some calculation for them, and that groups actually need to send their information also to the neighboring group. That's why they have a kind of coupling here. So we cannot separate them based on what they call it domain. So if we can separate them or decompose them based on the domain, then we can calculate for the plants alone and for the other group alone separately, like that. But in this case, we cannot split them. We cannot separate them from each other. That's why we need to calculate for them together as a one task. Then maybe the second task will calculate for them together in different stage or maybe in different time and so on. Actually, those examples are coming from the textbook. That's why I don't know why they try to take this kind of examples for computer science people. I don't know. We even doesn't understand sometimes what's the meaning of things like a molecular or something like that. We don't know how they calculate it. So
Doctor,
yes.
can you explain back the first statement? Each program calculates.
Actually, it's very complicated for us because we are computer scientists. We doesn't know what they do, what they mean by this. Actually, they calculate the population of a given group. So maybe they mean by population here the number of planets, maybe, or the number of whatever in the second group and the third group. I don't know how they calculate it, but there's something very important condition here, that where each group growth depends on that of its neighbors. So each group cannot grow by itself. It will grow based on the other groups' information, right? So that means there's some relation between the groups. There's some relation between the data, the groups of data. That's why they cannot, decompose based on data or based on domain. They cannot decompose, make the plants in one chunk. They cannot, because the plant's population cannot be calculated by itself. It still depends on the other group and third group and so on. You understand what does it mean? This is the
Yes.
main point that they want to come to. That's why when I take the example of the university staff salary, is to make things simpler for you to understand. That's why I don't want to dig in deep for this example, because really it's very hard for us to understand, and we have to go and see what's the meaning of population, what they exactly need to calculate, because this one is very general. I think it's not clear, right? We don't know what they want to do actually. Until now I don't understand what does it mean the population growth is based on the other group's growth. I don't know really. I have to read about this, which is related to different field of maybe science, or a different field of knowledge, which is out of my computer science field, right? That's why don't waste your time here. Just always keep in mind the scenario of the salary, the university staff salary. So if university staff salary system wants to be decomposed based on the domain, then they have to separate the data, like academic data is one chunk and non-academic data is different chunk. Then they run two copies of the program to calculate the salaries of the academic and the non-academic at the same time. But if they want to make it based on the function, then they don't have to separate the data from the database based on the domain, and they need to calculate the data, or decompose the data based on the function. The program based on the function. So tax function, tax calculation function, allowance calculation function, and main salary calculation function, and so on. Then each function would run in separate thread. Okay? So all of that stuff actually is a kind of repeating the same thing. We don't want to repeat ourselves. We don't want to waste our time. Okay? If the salary, the university salary system is not clear, let me know to explain it in different way. Maybe I use drawing, or I try to solve it in different way. Is that not clear, guys?
Okay, doctor.
Clear.
Okay, then we go to the signal processing. Signal processing here, they say an audio signal data set passed through 4 distinct computational filters. So if let's say here, when we receive a signal for something, maybe for radio, or maybe for audio, or maybe whatever, then we have to take that signal and we give it to 4 different filters. If the thing or the nature of maybe processing that signals based on that filters is sequential, then we cannot separate, or we cannot run them in parallel. Why? Because if the result of the first filter is the input of the second filter, then the nature of the program is parallel. So how we can make it, the nature of the program is sequential. How we can make it parallel? We cannot, right? But if let's say the same signal could go through multiple filters at the same time, and those filters are not related to each other, in this case we can run each filter in different thread. But in this case, if the output of the first filter is the input of the second filter, then in this case maybe we need to chunk the signals. The signal, we take the signal, we break it into many chunks, because here the signal is the data, right? So we break the signal into many chunks and we give every chunk to different thread. Then that thread will run the sequential filtering using the 4 filters as in the diagram here. Then after each thread finish, there's supposed to be another thread that collects all the results from all threads, combine them together to give the final result. Is that clear, guys?
Yes.
Is that clear? Yes. Okay. Actually, we have taken an example last time, which could be based on domain. Yes, this one, the factorial, is actually based on domain, because here the first thread calculates for the domain of 5 to 1, right? This the second thread calculates the factorial for the domain from 10 to 1, right? The third calculates from 15 to 1. The other one calculates for the domain of 20 to 1. So here the data is decomposed into multiple chunks, and the threads are based on the data, not based on the function, because the function, all threads will run the same function. They will run multiple copies of the same function, right? So this is what they call it, domain decomposition. Okay, let me go and check my the second example that we have run last time. Okay, let us close this. So close folder. Okay, then let us open. Oops. Let us open project. Okay, no problem. Courses, distributed, examples, application, this one. Let us see how this one is working. Okay, this one is also based on the domain, right? Because here what we want to do is to calculate the summation upper limit of those data, right? So here what we need to do is to give range of data, to the same function, right? To the same function. So what we are going to do here is to run multiple copies of the same function, but using different data. So here the decomposition is based on the domain. But what if we have, for example, let me open the this one. So let us for example say that we have data 1, 2, 3, 4, like that. For example, 1000. Okay, suppose that this is the data, but we have 2 tasks. For example, the first task is to calculate the summation of all data. Oops. Function 1 calculate sum of all data. Then here function 2 is to calculate the factorial of all data, right? Okay, is there a relation between the first function and the second function?
No.
There is no relation, right? Because the first function doesn't wait for anything from the other function to calculate, right? And also the second function doesn't wait for any result from the first function to calculate, because both of them could have the series of this range of numbers, and this function could run to calculate the summation, and that function could run based on the same data to calculate the factorial. And both of them could run at the same time, concurrently, right? So in this case, is there a chunking of data here or partitioning of data? There is no partitioning of data, right? But the partitioning here is based on the function. So we can run the function one in different tasks on one thread, and the second function on different thread, right? And both of them could work at the same time. So here, this decomposition is based on the function. Okay, guys? Is that clear?
Clear.
Okay.
Yes, maybe tomorrow we take, because now time is almost finished of this class. By the way, guys, tomorrow I'm not going to be around, so our tomorrow's class will be cancelled. So maybe I would try to record a video to explain the functional domain decomposition and domain decomposition tomorrow. I will try to record it and share it on YouTube. Okay, guys? Yeah.
Okay, doctor.
Okay, doctor.
Okay,
Yeah, but you still need to record your attendance, because it's allowed, based on the university rules, it's allowed to make class as a video. So don't worry. I will open the class for you tomorrow. Then you can sign your attendance or record your attendance. Then later I will share with you the video, and that video will help you a lot, and you can use it as a reference. Okay. We also need to decide the time of our test 2. We still have test 2. We still have assignment. Many things to do, actually. Okay. Let us stop here, or if let's say let us complete the climate modeling here. So the climate modeling here, they have each model component can be thought of as a separate task. So here they have atmospheric model, then they have hydrology model, then they have ocean model and land surface model. So all of that stuff could be separately working. So arrows represent exchanges of data between components during computation. So the atmosphere model generates wind velocity data that are used by the ocean model. So the ocean model generates sea surface temperature data that are used by the atmosphere model, and so on. So combining those two types of problem decomposition is common and natural. So sometimes what they want to say from here, they want to say that sometimes you can see that there is a combination of domain decomposition and functional decomposition. So, okay, here. Let us take this example. So if this is the example, what we can do here, we can use hybrid mode. So we can separate the data or split the data into two chunks. So the first chunk is until 500. Sorry, this is data chunk 1, data chunk 1, like that. And here data chunk 2, data chunk 2, it will be from 501, 502 to 1000. Okay. Then after that, we make copy of function 1 and copy of function 2 here. Then we take function, or maybe thread 1, for example, will run function 1 of chunk 1, like that, and oops, I don't know why this does not work. Okay, like that. And here thread 2, for example, function 2 of chunk 1, and here they have thread 3, for example, function 1, chunk of data 2, and as you could imagine, thread 4 with that function 2, chunk of data 2. Okay. So if you can see here, we have two types of decomposition. The first type here is based on domain, because we separate the data into multiple domains, right? So the first domain is from 1 to 500, and the second domain is from 501 to 1000. Then after that, we have another decomposition which is based on the functions, right? So this is a functional decomposition. So here's based on the function 1, and this is based on function 2, right? Is that clear, guys?
Yes, Doctor.
Yes, sir.
Yeah, please, if there is any question, I'm ready to help you. I'm ready to explain. Even if something that I explained before, I can re-explain for you guys. The important thing for me is to leave the class after you understand everything. Again, do you have any question?
No, Doctor.
So we are going to stop here. Let me insert something to remind myself next week. So we stop here. Okay. Okay, guys, then I see you. Thank you for attending my class. Don't forget to find the things on the YouTube channel. I'll try my best to record the video of last week, maybe today or by tomorrow, inshallah. And also for the tomorrow's class, I will record for you a video and share it on the YouTube. So please follow the updates on the YouTube channel, and inshallah see you next week. Okay? Assalamu alaikum warahmatullah.
Waalaikumsalam. Thank you, Doctor.
Salam,
Thank you,
Doctor.
Doctor.
Thank you,
Thank
Doctor.
you, Doctor.
Thank you, Doctor.